What causes issues in operational amplifiers, op-amps? Operational amplifiers are essential components in electronics and embedded systems, but they can face several issues that affect their performance. Let's break down what can go wrong with these devices. First off, operational amplifiers have a specific input common mode voltage range. If the input voltage goes beyond the power supply limits, it can lead to unpredictable behavior. This is especially risky during the power-up phase when input signals might appear before the power supply stabilizes. Such violations can cause the device to latch up, which means it gets stuck in a high current state, potentially damaging the chip. Next, we have input bias currents and offset voltages. Operational amplifiers need a small bias current at their input terminals to function correctly. If there is no proper direct current path for this bias current, it can cause voltage drift over time. This is particularly problematic in integrator or high-impedance circuits, leading to output saturation and signal distortion. Input offset voltages, which are tiny voltage differences at the input, can also contribute to errors in the output. Improper power supply and grounding can create more issues. If grounds are poorly connected, it can lead to ground potential differences. This can cause output voltage swings between supply rails. It is crucial to connect the non-inverting input to a stable reference point to avoid saturation and noise. Additionally, unused operational amplifiers in multi-op-amp packages can lead to excessive power consumption and overheating. Leakage currents can also be a problem, especially in high-input impedance operational amplifiers. These devices are sensitive to leakage currents that can arise from poor insulation or contamination on the circuit board. Even small leakage currents can create interference voltages larger than the input signal, resulting in noise and inaccurate measurements. Thermal and electrical stress can cause permanent damage to operational amplifiers. Excessive supply current, overheating, and electrical overstress, such as short circuits, can lead to common failure modes. These include output pins stuck at supply rails and gain reduction, which can affect the overall functionality of the device. Lastly, noise and interference can degrade the performance of operational amplifiers. External electromagnetic interference and internal noise sources can disrupt sensitive measurement and control circuits. Proper layout, shielding, and filtering techniques are essential to minimize these effects. To tackle these issues, engineers should ensure input signals ranges within the allowable voltage ranges. Providing direct current paths for input bias currents using appropriate resistors is vital. Proper grounding techniques can help avoid ground loops and potential differences. Designing for thermal management is also important to prevent overheating. Selecting operational amplifiers with suitable input, impedance, and noise characteristics for specific applications can make a big difference. By understanding these factors, engineers can design more stable and reliable analog circuits using operational amplifiers.